Today I am glad to talk about our work, ASCNet, Self-supervised video representation learning with appearance speed consistency. First, I will introduce the background of self-supervised video representation learning. Video analysis has become one of the most active research topics. However, high-quality video data with labels for analysis requires massive efforts of human annotation, which is hard to scale up. In contrast, millions of unlabeled videos are freely available on the internet. Thus, learning meaningful representations from unlabeled videos is crucial for video analysis. In self-supervised learning, the proper learning objectives are set to obtain supervision from the unlabeled data themselves. These objectives are called pre-text tasks. Unfortunately, some challenges still exist in self-supervised video representation learning. First, videos contain rich spatial information, for example, the background scene and the appearance of objects. Also, videos contain rich temporal information, such as the movement of humans and objects. These forms of information are helpful for downstream video understanding tasks and hard to learn simultaneously. Second, since videos have no annotations, it is challenging to get proper supervision signals for representation learning. So, the pivotal problem to solve is how to get supervision signals from the video itself to learn both motion and appearance features. Most previous works attempt to solve the challenge by designing pretext tasks, including future prediction, temporal order sorting, playback speed prediction, and so on. Particularly, the playback speed prediction task brings an effective supervision signal due to its nature of paying attention to the movement of objects. To be specific, video can be sped up by adjusting FPS and the speed can be the label. This task improves the quality of motion features extracted by the models. However, there are some limitations for existing pretext tasks. First, some of the approaches rely on pre-computed motion information, for example, optical flow, which is computationally heavy, particularly when the dataset is scaled up. Second, while negative samples play important roles in instance discrimination tasks, it is hard to maintain their quality and quantity. Moreover, same-class negative samples can be harmful to the representations used in downstream tasks. We observe that the consistency between positive samples is the key to learn robust video representation. Given a set of unlabeled data, we sample a collection of video clips at different playback speeds and apply different argumentations. Then, we use an encoder to extract features for each clip. We designed two pretext tasks to encourage models to capture the consistency between clips. The first task is named Appearance Consistency Perception, or ACP. Since different data augmentations and playback speeds do not change the content of the clip, we expect the appearance features to be always similar. The ACP task aims at capturing this consistency. We implement this by minimizing the representation distance between two augmented clips from the same video. Following BYOL, we use an online encoder and a target encoder, projection heads, and an additional predictor on top of the online branch. Then we achieve the goal by minimizing the L2 loss between the output representations. The other task is named Speed Consistency Perception, or SCP. Direct prediction of speed may be suboptimal because the changes of some motion may not be obvious under different playback speeds. So we only minimize the distance between the same playback speed. The implementation is similar to the previous one, except that the predictor and projection heads are independent of those in the ACP task. Compare the speed of unrelated videos does not make much sense, so we propose an appearance-based feature retrieval framework to collect similar videos for the SCP task. We evaluate the effectiveness of our ASCNet on downstream action recognition and video retrieval tasks. We pre-train models on the training set of the Kinetics 400 dataset and fine-tune our ASCNet on the first training split of UCF 101, HMDB 51 with labeled videos for downstream task evaluation. We compare our method with the state-of-the-art self-supervised learning methods. In Table 3, we compare experiments with different evaluation protocols used in prior works. In Table 4, we show the effect of pre-training epochs. For a fair comparison, we list our ASCNet trained with two common architectures in Table 2 to compare with SOTA. Our ASCNet achieves the best results over the two datasets under two settings. Remarkably, we achieve 90.8% accuracy on the UCF 101 dataset, which outperforms the pre-trained model fully supervised on ImageNet. We also compare our ASCNet with SOTA methods on the nearest neighbor video retrieval task. Our method surpasses all the considered SOTA methods and achieves the highest accuracies under different values of K. In conclusion, we proposed an unsupervised video representation learning framework named ASCNet, which leverages the appearance and speed consistency between videos. We also propose an appearance-based retrieval strategy to reduce the conflict between the appearance and speed consistency perception tasks. Extensive experiments show that the features learned by ASCNet perform better on action recognition and video retrieval tasks. Thank you for watching this video.